We're very excited to have Professor Surya Ganguli here with us, and he's done some really interesting work on understanding deep networks. He's a professor at Stanford, and as you can see from his affiliation slide, he has very interesting, diverse backgrounds spanning physics, neurobiology, electrical engineering, and we're very excited to hear his perspectives on language models and transformers.
Okay, thanks a lot. Yeah, so I talked to Umesh before giving this talk, and he wanted to kind of give like a little bit more of a broad overview of the field, open questions, and all that kind of stuff. And also I'll weave in some of my research. But I wanted to start from like what we really like is we'd like a theory of how all of the crazy stuff that's happened to us in the last couple of years works. And it's useful as a contrast to think about, say, general relativity, which I actually studied here as a grad student when I was doing my PhD here in string theory. It's perhaps one of the most elegant theories ever discovered. It can be encapsulated in a single equation. Right? On the left-hand side is the curvature of space and time. On the right-hand side is the stress tensor of matter. And so you can summarize this as matter tells space and time how to curve. And there's a second equation, the geodesic equation, which can be summarized as the curvature of space and time tells matter how to move, right? It's simple, it's elegant, it's incredibly precise and quantitatively predictive. It holds in regimes far beyond human intuition, right? Now, what do we have today with deep learning and ChatGPT and LLMs and so forth? So here, I love doing this. It blows my mind every time. Here's a ChatGPT prompt that I put in, which is explain Einstein's theory of general relativity in the style of Shakespeare. And it's incredible, right? It starts off in the realm where stars do hang and planets dance. Einstein, a sage of time and space's expanse, did cast his gaze upon the cosmos vast. And there a theory of great weight amassed. And you go through it, and it actually explains general relativity in a very poetic way. Just the final stanza. So next thou gazest upon the night's face. Imagine space-time in its endless grace. For Einstein's vision, vast and deep and wide, reveals the dance where mass and light abide. Right? It's incredible. What would it take to actually understand what happened here? Right? I mean, we're so far away from any of this, understanding any of this. So we're kind of pre-theory at the moment. Maybe the closest analogs are, in the 19th century, right? Engineering has far outpaced theory. And that happened, for example, with steam engines, but eventually we developed thermodynamics and statistical mechanics. Then we had engineered communication networks, and eventually we developed information theory. And now we have these engineered neural networks, and we need a theory of learning and inference and reasoning and so forth. But we're so far from that. But it's exciting. It's an opportunity. It can be. You can alternate between despair and hope in this field as a theorist. The way forward, when faced with such a gargantuan task, we all come from different communities with different practices. And I think in the way forward, just sociologically, we should be incredibly kind and understanding of each other's communities and be open-minded, right? So if you think about various ways of knowing, in theoretical computer science and math, the gold standard is a theorem and a proof in the most general setting possible. In machine learning, the gold standard is just improve performance, to the point where if there's no state of the art, then reject the paper, right? In physics, we often try to understand toy problems using heuristic analyses in scenarios where current math cannot yet deliver proofs. But we also try to extract testable predictions, which we can confront in actual systems where those predictions might hold beyond the toy settings that led to those predictions. And also there's an incredibly important role right now for careful scientific experimentation that reveals striking regularities without requiring any theoretical explanation whatsoever, right? Yes.
Summarize this in one. Okay.
Yeah. But also different types of theorists to be kind to other types of theorists, right?
No, you can't do that.
But this shows up in the reviewing process, right? Like you get all this weird anyways. You've all been through this. We don't need to have a therapy session on this, but I just we're all in this together, and to make progress, we really have to learn from each other and be kind to each other in the reviewing process. All right. So I'll talk about, in a slightly idiosyncratic way, just various aspects of theory. In many cases, we don't have theory for the systems that we want to have theory for, LLMs, so I'll fall back on simpler systems. In other cases, I'll try to confront the systems directly. And also Umesh mentioned that maybe some connections to neuroscience might be interesting. So I'll end with that at the very end. Okay. So the first regularity that really captured the imagination of industry and academia alike are these scaling laws, right? They motivated huge investments in compute, data collection, and so forth. And these are, the error tends to fall off as a power law with either the number of parameters, the number of data points, or the amount of compute. But my opinionated take on these scaling laws is that they're quite incredible so far, but they're unsustainable going forwards because the exponent is so small. So advancing AI through scaling alone is expensive and unsustainable, I think. And there's got to be a better way. We don't have it yet. But because it's the only game in town, the companies are doubling down on this. So for example, here's a scaling law where this is the test loss or perplexity as a function of, say, data set size for a transformer. And dropping an order 1 amount of nats requires about 10x more data, though this is sort of an exponential measure right here. Okay, and the exponent is minus 0.09, so it's quite close to 0. Okay. In large vision transformers, going from 1 billion to 2 billion data points leads to a drop in error of about 2 to 3% performance on ImageNet. And now, having said that, there are surprising properties that emerge at scale. I'm just saying, going forward, is this really the best way forward, or can we do better? And I hope we can do better. Just as a point of comparison, if you think about the amount of data in words that GPT-3 ingests, it would take a human 20,000 years to read that same amount of data. So humans are much more sample efficient than GPT-3, and a human plus Google search can be relatively powerful compared to GPT-3. Although, again, there are these weird things of creativity where I could have never come up with this poem as quickly as GPT did. So there's a very strange pattern of performance and fragility in these systems. So what do we know about theory and scaling laws? So a bunch of physicists have worked on theories of scaling laws. They're, of course, originally discovered by Kaplan, originally trained as a particle theorist. Here's a bunch of works. I'll just talk about one that's pretty insightful and quite precise. And it actually recovers a lot of the qualitative properties of scaling laws in LLMs and transformers and so forth. But they work it out on a toy model, which is the random feature model, right? So this is this paper led by Cengiz Pehlevan and Blake Bordelon and Alexander Atanasov. So here what they do is they have data generated by a teacher random feature model. So this is a model where you have inputs X that are fed through fixed nonlinear functions psi. These are the features. There's a dot product with a true teacher weight vector, and there's some noise, so that the outputs are noisy. So this generates the data. This is a model of the data. And importantly, there's a distribution of inputs, and the covariance matrix of the features, i.e. the kernel matrix, on average has an eigenvalue spectrum given by these, or at least it's diagonal here, so these are the eigenvalues, right? So the kernel matrix of inputs has a non-trivial eigenspectrum, and this determines a lot of the properties of the learning curves and so forth. Now, this data trains a student random feature model of the same form, so it has the same random features, fixed size, that are not learned. And then there are these weights here, okay? So, okay, and what they can do using techniques from statistical physics is they can compute learning curves as a function of the spectrum, the number of features, the number of data points, and so forth. And the take-home message is that if the kernel matrix of inputs has a power law spectrum, i.e. the data has a power law hiding inside of it, then you will get power laws with respect to model size, compute time, and data set size. And the exponents of these power laws are all computable in terms of the exponent of this power law hiding inside the data. Okay, so that's a really nice result. And it's not unreasonable, actually. Like if you imagine a huge text of language from the internet, it might have a lot of one type of language in it, a little bit less of another type of language, a little bit less of, say, more esoteric language, and so forth. So there's kind of a power law decay of different types of examples in the large training set. And you just need to increase the amount of data to sample the less and less frequent items, right? So then if there's a kind of a power law spectrum of different types of data, the overall perplexity might scale as a power law with the amount of total data. It's not an unreasonable model, and it's actually analytically exact. So they get, at least for this toy model, right? And the dependence of the exponents as a function of data set, model size, and so forth, has similar properties to what you see in LLMs and transformers. So that's kind of interesting. We actually played this game also in this paper here, not for random feature models, but linear regression, but they're very similar. So L2 regularized regression, and you can get really funny curves that are kind of interesting. So what we did, we had a similar setup, but with a student and teacher setup as before, but with linear regression, with L2 regularized linear regression. So there's a regularization aspect to it in high dimensions where you have an arbitrary covariance matrix of input. So it's not a IID Gaussian, well, it's a Gaussian design, but with an arbitrary covariance matrix and a potentially arbitrary alignment of the teacher weights to the eigenmodes of the covariance matrix. And in a situation where a covariance matrix doesn't have a power law scale, but it has a power law spectrum, but it has a multi-scale spectrum where you have many large eigenvalues, many smaller eigenvalues, and then many smaller eigenvalues that are clustered together. So you have multiple scales in your data. Then you can get learning curves at fixed regularization parameter that exhibits multiple descent phenomena, right? So you can get triple descent, quadruple descent, and so forth. And where this horizontal axis is the amount of data, this is the test error. The solid curves are analytic theory, and the dots, which you can barely see, are numerical experiments. You get an exact match between theory and experiment. And you understand what's happening. Each of these peaks occurs when the amount of data increases. And as you increase the amount of data, you suddenly first see the largest scale, and you get this peak. You next see the second largest scale, and you get this peak, and so forth. So the number of peaks corresponds to the number of scales in the data. The usual double descent for linear regression only has one scale, so you only see one peak. Okay. Now this holds at a fixed value of the regularization parameter, but whenever you get worse performance as you increase the amount of data, you must be doing something suboptimal. One second, I'll just finish this So if you choose the optimal L2 regularization weight as a function of the amount of data that you have, then you get these red curves and you get monotonically decreasing behavior. And so all this multiple descent disappears. Okay, yeah.
Just so you don't lose me on slide 5.
Yeah.
The student-teacher setup that you mentioned,
Yeah.
should I think of it as a sample out of a population?
Yeah. Let me go through that slowly, because the student-teacher setup is very common in physics analysis and also in statistics analysis. So statisticians, what do? They assume some generative model of the data that's under complete mathematical control. They have some learning algorithm that ingests data and plots a predictor, spits out a predictor, and they want to compute the test error of the predictor. That's exactly what's going on. This is the generative model of the data. We call that the teacher, and then this is the student, which we train. Right? Yeah.
Thank you so much. This is so cool. For the distinct descent regimes that you were talking about, do these denote like separate phases, like phase transitions in?
They're related. So what happens is, if you think about the covariance matrix, the empirical covariance matrix of your data, as opposed to the true covariance matrix that generates your data, that empirical covariance matrix undergoes a sequence of phase transitions. So that's what I had here. And so there are these sequence of phase transitions in these related to the so-called multi-scale Wishart random matrices. And the phase transitions in your empirical covariance matrix control these peaks in the multiple descent. Right? Yeah.
Sorry, follow-up question. From my very limited understanding in statistical mechanics, they often talk about phase transitions as a result of like broken symmetry, and I don't research on this.
Yeah, here it's not quite broken symmetry. It has to do with phase transitions in random matrix vector, which is phase transition generally is just a sudden change in a property as you continuously vary a parameter. So you get phase transitions in the spectra of these empirical covariance matrices.
Gotcha. Thank you.
Okay. Some other work that we did recently is you don't have to be content with power law scaling, right? So for example, if you think about power law scaling with respect to data set size, slow power law scaling with respect to data set size indicates that training examples are highly redundant, right? If you pick a random 1 billion sentences, chances are the billion plus first sentence or the billion plus first image is not going to tell you anything new compared to the first billion, right? So, and it turns out you can show analytically in simple settings that redundancy is the origin of power law scaling with small exponents. Power law scaling of test error with respect to data set size with a small exponent. So then maybe we could try to prune data sets or find prune data sets to identify sparse subsets of non-redundant examples, right? And if we plot error as a function of the size of a pruned non-redundant data set, we might be able to beat power law scaling, right? And we show analytically that we can do this in theory for perceptron learning, in again, a student-teacher setting. And we can there at least achieve exponential scaling. And then we show how to beat, in practice, power law scaling for vision problems. And actually, a really interesting open problem is, can you beat power law scaling for language problems? We actually haven't worked on that problem yet. I'm suggesting to some students that we should think about that soon. Yeah, I'll do this in more detail, but yeah. I'll go through in more detail and ask if I don't answer that. Yeah, pruning has to do with selecting subsets of data, and then with that non-redundant subset, you train as usual. Yeah. Oh, pruning. Okay, so there's various ways to do it. You can use a pre-trained foundation model to prune, or you could train for a short amount of time and use data from that short training run to prune. The idea behind this thing is you can actually invest a lot of effort in finding a really good non-redundant data set that then can train many, many different foundation models. So you can amortize the computational cost of pruning into the gains that you get from training on a smaller data set later on. Potentially, yeah. Yeah. We give the philosophy of how this might be useful in the paper. We call it a foundation data set. Mimicking my Stanford colleagues on foundation models. But okay, so this is the paper if you're interested, and here's some precursor and follow-up papers. I don't know how much detail I want to go into this, but okay, so again, mimicking the student-teacher setup. So here's the theory where we can prove that you can beat power laws, right? So you have a teacher setup where you just have a perceptron, right? It computes these are the teacher weights of the teacher perceptron. So it has a decision boundary in say n-dimensional space. The examples with a positive dot product in the weight have a +1 label. Examples with a negative dot product have a -1 label. And that's it. That's your teacher perceptron. The examples are Gaussian. The inputs are Gaussian. Okay. The data pruning strategy is to train a probe student for a short period of time. It may not align with the teacher. And then you want to keep the hardest data with the smallest margins with respect to the decision boundary of the probe. Okay, this is motivated by some existing work on pruning, actually done by ourselves and others. And then the idea is you keep only the hardest examples, and you train another student from scratch on the hardest examples. Okay, and so. And then you try to analytically compute the test error of a max margin learner on now the non-Gaussian pruned data. The data is non-Gaussian because you've sub-selected data points according to their margin. Okay. Okay, so you have an amount of data, and we're working in the usual high-dimensional statistics limit, where the number of parameters of the dimensionality is going to infinity, the number of data points is going to infinity, but their ratio is order 1. So you start with a total amount of data, alpha total, but you keep only a fraction of data according to this pruning rule. So you get a data set size of size alpha prune, right? Normalized by the dimension. Let me skip the details of how we do it, but this is the math, all right? And here's the results, okay? So again, just to illustrate how we can get complete theoretical control of the situation, the solid curves are theory, and the dots are simulations, right? And there's, of course, you can see there's a nice match. The colors indicate the fraction of data that we keep under our pruning algorithm. So 100% data is just normal training, right? And this has a power law with exponent -1. But now what we could do, and this horizontal axis is telling you how much data is there in the pruned data set, right? So now there's many ways to get a pruned data set of a given size. You could start with an extremely large data set and do aggressive pruning, right? That's like here, right? So you start with a very large data set and keep 10%, or you could start with a smaller data set and do no pruning, or slightly smaller data sets and do slightly more aggressive pruning. Okay, so that's is what gets you this family of curves, and the Pareto envelope is actually falling off exponentially. So this suggests that as you get more and more data, prune more aggressively, and you can get like an optimal data set of a given size. Okay? And so let me skip these details. And so we then tested this prediction. For us, this was a prediction because we didn't realize that we could probably beat power law scaling in realistic settings. We realized that we could beat it in the simple student-teacher setting. So we asked, can we use the same principle, keep the hardest data points after training for a short period of time, where now the hardest data points are the ones closest to the decision boundary in the final layer, right? And we saw that following the same procedure, we saw that the Pareto envelope could beat this power law that you get in vision tasks in these settings. And then I won't discuss the rest of the paper, but we showed how to make pruning efficient if you have a pre-trained foundation model. You can use information in the foundation model, so representations, to find outlier examples, and then train only on the outlier examples, and you do better than if you train on random examples. Okay. And then eventually, in this paper, connecting back to language vision models, we were able to double the efficiency of training of clip models trained on lion data sets. So the lion data set is a paired data set of about 400 million, depending on which subset you choose, 400 million paired text image examples. And it learns a multimodal model for text and image, an embedding model. We could show that there was a lot of redundancy in this data set, and we could reduce it by half and therefore speed up training by half. Without sacrificing or reduce training time by half without sacrificing performance. Yeah. Yeah, I erased that slide for this talk, but we were actually able to compute the information gain that you get from adding one new example. We can compute that analytically in the student-teacher perceptron setting. And we showed that the information gain decays for a random data set, but asymptotes to a finite quantity for a pruned data set. And so if the information gain asymptotes to a finite quantity, each new example multiplicatively reduces your error, which leads to the exponential decay of error. Yeah, so that's in the paper, in this paper. Okay, so again, here's a simpler setting again for vision tasks where we can bend power laws down to exponentials. I would love to do this for language. We actually haven't even started to think about that. But I think the way forward there would be to think about it in toy settings, which I'll talk about next. Yeah.
If you're using a foundation model to prune, that foundation model is taking a lot of data, right? So,
yeah.
I mean, there's some information that you're actually giving, the foundation model has, and then you're using to prune that data set. So is it actually like, is it a fair thing to do? Because you're taking a big data set and then pruning it and saying that.
So fair compared to what, right? So if the practical use case would be, the foundation model is already sitting there. Somebody's already spent that money. It's a sunk cost. But like, can I then reduce the data set? And then for all subsequent foundation models I want to train in the future, I never have to use the original data set, right? So that's like what we did for Lion, right? We said for Lion, we used a trained clip model to half the data set size. And that data set size was really, really good at training subsequent foundation models, right? So that's what I'm saying is you might not need to worry too much about the computational cost of pruning if you get a really good data set that many, many people can use for many downstream purposes. Right?
So you need some way that you can't use the original foundation model, but you want to train a new foundation model with some other data, then it's the use case.
Exactly.
You could have just used the original foundation.
You could have used the original foundation. Exactly, yeah. So people are always iterating on training of foundation models, right? So that's the use case. It's like the OpenAI playbook. We're going to build it, and we're going to hope we're going to make money. Maybe I shouldn't have drawn that analogy actually for myself, but anyways, yeah, that's kind of the rough use case. But also for us, it was more of really a scientific question. are we doomed to power laws, or can we beat them? Right? Yeah.
Would there be a way to like prune data without already having a pre-trained foundation model?
Yeah, so that's what we did here. In these settings, what we did was we trained these convolutional networks on the data set itself for a short period of time, and we found the hardest examples according to the decision boundaries there.
I also wonder if the observed trend is applicable to all types of the data sets. So, assuming let's consider we have a very stupid language model and always memorize stuff, and so we have 3-digit multiplication, and it needs to cover like 90% of the case to make it like generalizable or test set, I assume. So I just wonder if you make the prune on this case, like how do you do the prune? And if that's still applied to this case, I mean, it's analogous to the large language data set because lots of the scattered facts.
Yeah.
So I wonder if the pruning can be actually.
I mean, for there, I think there's already a question: does the training itself even work? Right? Like these systems are really bad at length generalization, right? They're really bad at deep logical reasoning. They tend to take shortcuts. So there with these LLMs, we're already starting with models where they might not actually work the way we think they do, right? Yejin has a great paper on faith and limits that shows that they're terrible at reasoning, though they can fool us into thinking they do valid reasoning by taking shortcuts. So I'm not sure. The answer to your question is an empirical question. Yeah.
So this reminds me a lot of these approaches in medicine and statistics on responsive design or adaptive testing, or like in medical trials when you try to limit the number of people that you take in an addition. And to see those, what is a useful next case that
Yes, yeah.
It's just that you start with the population or with your...
Exactly, yeah.
So can you do it from what the work you've done? Could you reverse it and learn, if you start a new one, you don't have the population, but you can learn, is it worth taking in new data, or am I done?
Yeah. There's a whole like continuum of procedures of increasing sophistication, right? Active learning, for example, is where you decide which example you want to ingest. You could think of this as one-shot active learning, starting from the population, deciding a subset, and then going from there. But you could do iterative active learning, where you train and then pick, train and pick, train and pick. So there's a whole continuum. Yeah, it's been quite difficult to get active learning to work in deep learning, usually because usually approaches to active learning depend on having a good sense of the uncertainty in different parts of input space of how well you're doing. And it's notoriously difficult to calibrate networks to have good estimates of their own uncertainty. Ensembling is one way to do that. So you train a bunch of models and you pick the examples for which the models maximally disagree, and then you train on that one, right?
And you don't need uncertainty as a...
We don't need any, we do, in the sense that we compute distance to the decision boundary, but we don't explicitly use the probability, but we do use distance to the decision boundary, which depends on the probability. Yeah.
Somehow this should be connected with from the question that you asked about the multiplications, connected with compression, how to compress data. Because we have billions of examples of multiplications, but I just need minimal instructions to
See, you want to learn the algorithm, right? Like when I teach my son multiplication, I don't give him billions of multiplication problems and say, this is the answer. 54 times 36, this is the answer. We don't do that. We just communicate the algorithm. I think this is the sense in which we might be doing everything completely wrong right now with LMs and reasoning, right?
just instruction. This is the simplest one.
Yeah, I mean, I teach my son math in much less examples than LLMs need, and he's not bad at it, actually. And he length generalizes because he knows the algorithm, right? That's the key. We need to teach them the algorithm explicitly. But then we get into symbolic AI and we lose the learning aspect of it. So it's putting together symbolic AI and learning is a major challenge, I think, for the future. Okay, so oh, sorry, I had, the moral of the story so far, popping up a little bit about, Umesh asked me to give a kind of a broader perspective. So the moral of the story so far, I think, is that the structure of data itself is the dark matter of theory and deep learning. What do I mean by that? we will never really understand what deep nets or transformers or LLMs are doing unless we understand what we're asking them to do. And what we're asking them to do is embedded in the structure of the data itself, right? And of course, the loss function. Right, so one route towards progress, now we don't really understand the structure of language, we don't understand the structure of images. So then one route to progress would be to make toy models of data and understand deeply how transformers and LMs work on these toy models, like these student-teacher generative models we've been discussing in simpler settings. Another route to progress might be interpretability studies on generative models of data themselves, which ironically are our current best mathematical models of natural non-toy data. Stable diffusion and other diffusion models might be our best model of natural images right now, right? So we need to understand how they go from Gaussian noise to images and how structure is built in, and maybe that will teach us something. Okay, so going back to the outline, so now the importance of data and toy models of it. Okay, so in the context of language, LLMs, and for this thing, what are good toy models of language? Well, a reasonable starting point is probabilistic context-free grammars. You've all encountered these in grammar classes, right? So you know, you can have these parse trees where you have these internal rules of expansion or production rules. So a sentence, anyway, the sentence goes through a noun phrase and a verb phrase and so forth. And a probabilistic context-free grammar induces a probability distribution over these production rules. And these production rules terminate at terminals, which are individual words, nouns, verbs, and so forth. And then you generate sort of valid sentences. At least under this framework, they'd be syntactically valid, though not maybe semantically valid. Okay, so this creates an interesting mathematical model of sequences with interesting temporal correlations. Okay, and there's been a bunch of work like trying to understand how RNNs and transformers model these. So here's some work that I was involved in, led by Jonathan Hewitt, where for context-free languages of bounded depth, we came up with an explicit construction of an LSTM that can generate such languages. And it mimics a stack machine, a stack automata. So to parse these languages, you need a stack. In the Chomsky hierarchy, these context-free grammars corresponds to stack automata, right? So we just mimicked a stack in this thing. And we could also lower bound the size of any LSTM that can generate a particular context-free language called the Dyke-KM language that corresponds to all well-formed parentheses of k different types with a maximal depth of m, right? So this is an example of a well-formed parentheses with 2 types and its parse tree. Okay, there was follow-up work, very interesting follow-up work by this team, where they came up with an explicit construction of a transformer that can generate Dyke-KM languages, and so forth. So that's kind of interesting. They're starting to get an intuition of how transformers can process language. Here's a really interesting paper by Sanjeev Arora and colleagues, where they asked, do transformers parse while predicting the masked word? So, you know, there's 2 types of LLMs, of course. There's autoregressive LLMs, which predict the next word, and there's masked LLMs, which predict a masked word conditioned on all the other words, or maybe multiple masked words conditioned on the other words. That's what BERT does, right? So, so that's like computing conditional probabilities in language, right? So they asked, well, what if you generate an artificial language from a probabilistic context-free grammar, and then you try to parse sentences from that grammar? So parsing corresponds to taking the sequence of final terminals, the words, and computing a posterior distribution of production rules given the sequence, or computing the posterior probability of a masked word given all the other words, right? Actually, parsing would be an intermediate step in predicting any masked word. So it might stand to reason that BERT might implicitly do this probabilistic computation. So an algorithm for doing this probabilistic computation is called the inside-out algorithm. It's roughly like belief propagation in a probabilistic context-free grammar. And they did some nice things. They provided an explicit construction of a transformer that implements the inside-out algorithm. The catch was it was much larger than BERT. So given the complexity of the grammar, the number of non-terminals, the number of production rules, the number of terminals, they came up with a transformer that scaled as these various measures of complexity of the grammar scaled up, but it was too large for BERT, for a probabilistic context-free grammar that corresponded to an approximation of English. So then they suggested an approximation of the algorithm, and they also probed BERT trained on an English on a PCFG approximation to English. And they showed that they can decode intermediate quantities of the inside-out belief propagation algorithm from different layers of the transformer, providing sort of neuroscience evidence that that BERT-like transformers are parsing while they're predicting. So that was kind of interesting, I thought. There's also some interesting work by some physicists on PCFG's transformers and language learning by Mathieu Wiart, a friend of mine. So they also kind of followed the PCFG route, but with a fixed topology. So they didn't have to worry about the whole inside-out algorithm and all that. You just have a graphical tree of fixed topology. The leaves generate the sentences. And you get power law correlations as a function of the separation because of the hierarchical structure of the tree, right? So for example, this is correlated with this is correlated with this at a lower level, this is correlated with this at a lower level. So you have a sequence of hierarchical decay of correlations, depending on how close your most common, at least how close your most recent common ancestor is. So then he did an auxiliary calculation in this graphical model, which is to measure correlations at a certain level, how much data do you need? And that's a very simple, like, 1 over data set size calculation as a function of the correlations. And they said you need a certain amount of data to measure the correlation between here and here, more data to measure the correlation between here and here, more data to measure the correlation between here and here. That's a simple non-LLM calculation. Okay. Then what they did is they asked now you trained the system with different amounts of data, and you asked, how does the cross entropy loss decay, right? And so this horizontal and vertical curve, the black dash curve, is the heuristic theory that they got by saying, at this level, right, I have enough data to measure the strongest correlations. At this amount of data, I have enough data to measure the next strongest correlations and so forth, right? And then they could also estimate how well you'd get the cross entropy if you only got correlations of a given size. So they get the horizontal curves that way. And then they trained a transformer on data generated from this graphical model. And you can see these drops in the cross entropy loss at qualitatively around the time that they would have predicted it, just from a simple calculation of the probabilistic graphical model. So that was kind of nice, I thought. It's an example of how heuristics and approximations can get you a sense of what's going on without ever proving a theorem, without ever getting an exact match, but getting a conceptual insight, which is, of course, what we're all after as scientists. Yeah, so I hope, like, if you're a math person, you'd be kind to this paper. Okay, so the moral of the story for this part is there are things we understand very well. We understand probabilistic graphical models of sequences and other things, like also graphs. And we understand learning and inference in them. There's things we don't understand, transformers, how they learn and how they behave once they're trained. But we could try to bridge the gap by using graphical models as sources of toy models of data and mapping trained transformers to known learning and inference algorithms in these models. Teng Yu, I think, talked about some work on in-context learning on simple mixtures of HMMs and things like that. So that's another nice example of that. My colleague Noah Goodman formalized reasoning as probabilistic inference in a random graphical model. And multi-hop reasoning involves computing the conditional probability of one node given some other node where there's a minimal separation between them. And he could show that transformers did worse and worse on multi-hop reasoning as the separation between the nodes increased, unless you put in chain of thought into it. And there's some nice correspondences between what transformers do and what belief propagation in the graphical model does. So that was kind of nice. It's another example. Okay, so let's see. Okay, the next thing that kind of puzzles me, or I'm trying to think of the things that kind of amaze me about what's going on. The next thing that kind of amazes me is exponential creativity, which is what I call exponential creativity with polynomial experience. Okay, so just so that we're on firm theoretical foundations, let's talk about something extremely simple, right? A long sequence of n IID random variables, each taking k possible values. So think you have an alphabet of letters, k possible letters. You draw each letter in the sequence IID from some distribution, right? And you get a big long sequence, right? So now you think about what the distribution over sequences looks like, right? And the asymptotic equiprotection theorem says that the structure of P of bold letter S, where S is the n letter sequence, is very special and universal. It's roughly uniform over a typical set, right? So here's the typical set, right? And every sequence in the typical set has roughly the same probability. The size of the typical set is e to the n times the entropy of the single letter distribution, right? And therefore, and the entire distribution is concentrated on the typical set, and therefore the probability of each sequence is e to the minus n times S of p. And so this times this gets you approximately 1, and there's no probability mass elsewhere, right? Okay, so but of course the total number of sequences is much, much bigger, right? There's e to the n ln of k possible sequences of length n and alphabet size k, right? Otherwise known as k to the n, okay? So physicists, we like our exponentials, all right? So, okay, so now the take-home message is that for large high-dimensional data like this, the typical set is exponentially large, but it's also an exponentially small fraction over all of sequence space, yeah?
So because this is Euclidean space visualized. So the S sequence doesn't lie in that.
Yeah, this is a stand-in for like a hypercube of n dimensions with k points along each dimension. Yeah.
Just embedding distance, something like that.
Yeah. So, okay, so these last two properties hold more generally for natural images and language. If we think about images of a given size or sentences of a given size, the number of possible legal sentences grows exponentially with length. The number of possible images might grow exponentially as you kind of zoom out. But there's still the set of all possible pixel values and the set of all possible sequences of letters is a much, much larger exponential size, right? And so now these generative models for language and images, they do something remarkable, seemingly remarkable. They don't see the exponentially many possible legal sentences or legal images or natural images. They see some much smaller fraction of them, maybe a polynomial amount in the dimension or the length of a sentence. Yet, they seem to be able to sample many, 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 maybe exponentially many legal sentences or images and not sample the illegal ones, right? How the heck is that done? For this very simple case of IID sequences, it's super easy. All you have to do is estimate the marginal distribution, and then you have a generative process of IID sampling. So there you can easily do it. But for pixels, there's subtle correlations between the pixels. For language, there's subtle correlations between the words in language. And so how do you do it there? How do you get the correlations right? Okay. So that's what I call the problem of exponential creativity with polynomial experience. Here's an example of that, right? The famous one from Stable Diffusion of an astronaut riding a horse on the moon. Maybe I don't know if this is true or not, but there probably wasn't an image like this on the internet before Stable Diffusion dreamed it up, yet it was able to dream it up, right? Now I got this through a Google search, so this is all over the internet. But this is actually an open question. How creative are these generative models? Are they somehow combining training set images in some simple way to creatively generate a new image, and we can understand the process of going from training samples to new samples? Like, how can we do that, right? This has been bugging me. We have a way to do that now with diffusion models, and this is unpublished work. I'll just give you a teaser. I think I'm coming back in the future to speak, and so I could give a much longer talk on this in the future, but I'll just give you a teaser now with these diffusion models. So there are, by the way, diffusion models, of course, for images, but there's also diffusion models for language models as well. My colleague Tatsu, who I think spoke yesterday, has some diffusion models for language. So what does a diffusion model do, right? You have a forward diffusion process that turns a structured distribution into a Gaussian distribution, and then you learn the reverse diffusion process to go from a Gaussian to structured data. You can write down analytic formulas for the reverse process if you have access to the training data, which is a sum of delta functions over the training points, right? And so if you succeed in reversing the diffusion process, you get a process. You can show, this paper showed that you go directly from the Gaussian over time to a set of delta functions on the training points. That's all you can do. So if you fully succeed in solving the score matching objective of diffusion models, that's all you can do, which means all you can do is memorize the data. That means your Gaussian noise will reverse the diffusion process and go to one of your training points. You will never be able to generate something other than a training point, okay? So the very success of diffusion models in being creative and sampling new points that are not close to the training points relies on it not being able to solve exactly the ideal score matching objective. It's got to be regularized or inhibited in some way. Okay? That's, I think, an important lesson from this paper. So now, how do you theoretically come up with a framework for generating creativity in diffusion models? So we've come up with this. So how are diffusion models hobbled these days? Well, a backbone for diffusion models, yeah?
This goes down to saying that the maximum likelihood density is...
Yes, it's related to that, yeah.
Okay.
Yeah, it's related to that, but like the maximum likelihood estimator is a particular diffusion process that does gradient descent on the time-dependent score function of the forward diffusion process and so forth. So you write down, you have an explicit dynamical system for the maximum likelihood estimator. Yeah, but that's in spirit. It's exactly what's going on, right? But now the trick is, how do you go away from the maximum likelihood estimator in an intelligent way such that you sample this exponentially many things and don't sample this much larger exponential? Right? That's the question. Okay, so modern diffusion models, when Joshua and I first did the first diffusion model, we didn't use these sophisticated U-nets. We used a multi-layer perceptron, which actually, in hindsight, hobbled our ability to generate images as well. But modern diffusion models use what's called a U-net, right? So here's the Gaussian sample, and it goes forward like this to generate an image here. And it has a convolutional structure, this local structure, that compresses and then expands. These were originally used for image segmentation, but it's a very nice structure for turning Gaussian pixel noise into structured pixels. Okay, so this has a locality principle embedded in it, right? So we decided to come up with a so-called ideal locality, in your language, an ideal locality constrained maximum likelihood estimator. Okay, or a locality constrained ideal score machine that does gradient descent on the score function. And so what that does is it gives us an analytic ODE that we can just run to generate samples. So we start with noise and we run the ODE. Each pixel and its local patch is just doing gradient descent on the score function. So if that patch were left to its own devices, it would flow to a patch from one of the training set images and nothing else, okay? But that patch isn't operating on its own. There's, of course, other patches. So each patch is trying to pick one of the training set points. But there's nothing constraining, well, this patch over here, like if this is your big image, this patch here and this patch here could now go to different training set points. But it can't pick any set of training set points because the patches overlap. So you get these local constraints where pixels and overlapping patches have to be the same. So you basically build up an image by a jigsaw puzzle. One local patch might come from one training set point, another local patch from another local patch from another. But the patch-wise constraints give you global order, right? Now this is an analytic ODE that we can run, okay? It's totally interpretable. We understand exactly what's going on as opposed to what's happening in this complicated train unit. Now here's the kicker, right? We take a Gaussian noise sample and we feed it through our ideal score machine. The ideal score machine has access to all the training set points explicitly, right? So we feed it through that and we get a sampled image here on the left. This is very small, but it says theory here on the left, right? On the right, we train a U-net on the same set of training points, and then we feed the same new Gaussian sample into the U-net. And this is the sample that we get. And you can see that on a case-by-case basis, our theoretical machine predicts what the trained U-net predicts. I mean, there's small differences here, right? But we were super excited about this because to our knowledge, this is the first time that you could predict on a case-by-case basis what a trained diffusion model does, okay? Now, importantly, this diffusion model does not have attention in it. It's a convolutional-only diffusion model, which is why the locality-constrained ideal score machine is such a good approximation to it, we think. So this works well on simple data sets like MNIST and fashion MNIST. But if you try to go to CFAR 10, to model CFAR 10, you need a bigger machine, which involves cross-attention in here. And then the samples on CFAR 10 are good if you have cross-attention in the train U-net. If you don't have cross-attention in the train U-net, the samples are bad. But our ideal score machine predicts the samples, right? So in any case, here's an example where you really understand creativity. It's creating new digits that are not in the training set by mixing and matching different digits from the training set in a spatial way. My dream is that these like stable diffusion where you have a VQAE and it projects to a latent space and you do diffusion in the latent space. My dream is that there'll be a similar picture for creativity in these more complicated models, but the combination of training points is happening not in pixel space spatially, but in some kind of semantic space with constraints. Like you have an astronaut, you can make it sit, you have a horse, you can make the astronaut sit on the horse, right? Like that's kind of like how we're creative. We have all this knowledge and we try to combine it in novel ways, right? So that's my dream, is somehow in these more complicated diffusion models with cross-attention and latent spaces, can we uncover semantic rules of combination that allow us to go from the training set to a new sample? That's a dream. Like I have no idea how to do it. I think it's an interesting problem to think about. At least we have some purchase on it in the convolution-only setting for simple data sets. Okay, let's see, we started late, right? So what time should I finish? 12, okay, excellent, 12:45. Okay, another example of exponential capacity with polynomial experience is this sort of in-context learning for linear regression. So this is work done by this amazing team here. I think Teng Yuma talked about in-context learning, so I'll go quickly on that. But basically, in-context learning is you have a big LLM, you've trained it on the entire internet, and then you give it some examples of a task you want to solve. Like, you might say like Marie Curie, France, right? Like Albert Einstein, Germany, Newton, England, or something, right? And then you give it a new scientist, and you want it to spit out the country of that scientist's origin, right? So in context, you provide a few examples of the task. You maybe don't even explain the task, although in more sophisticated settings you do. And then you just give a new test example, and without changing any of the weights, the LLM can solve the problem, right? So again, it's a remarkable capability, right? Especially when it first came out. How do we understand it for language? It's very hard. So retreat to a toy problem where you can get purchase on it. Okay, so the toy problem was regression. We were actually following some work that was looking at in-context learning regression. And here the basic question is like, the basic question we're trying to ask is, can you solve fundamentally new tasks that were just not in your pre-training set? Okay, that's the question we're going to ask. So, okay, so here's the setup. So now you have an unknown true regression vector that generates your data. You get k input-output pairs, x1, y1 through xk, yk. The input data is drawn from a Gaussian, and the output is labeled by the true regression vector with some noise. Okay, so that's how you generate one batch of examples, one in-context batch. Okay, and then you pre-train a transformer on a bunch of regression tasks. And then once you have that pre-trained transformer, you ask it to solve new regression tasks in context. So this is an autoregressive transformer. So you feed in input, output, input, output, and it's supposed to predict the correct output for each of the inputs. Oh, sorry, it's given in context. It's given the output in the next step, but at this current step, while it's only seen the input, it's supposed to predict the output. So here's the in-context prediction, and then this is the right answer that's given as input, and then it's supposed to predict the output to x2 given x1 and y1, right? And then finally, it's supposed to predict the output to xk given x1, y1, x2, y2, and so forth, right? So that's classic in-context learning, but now just specialized to regression. Okay? and I won't go through, I think I've spoken about this once before here. And so I just wanted to just really like summarize the main result in a cartoon figure, okay? So again, the question is, when can a transformer solve a really new task in context? So of critical importance will be, well, what was the pre-training like? How many different regression problems did it see in pre-training, right? So if you think about the set of all possible true regression vectors, W, in d-dimensional space, the set of true regression vectors sit roughly, if they're normalized, they sit on a sphere, in a d minus one dimensional sphere in d-dimensional space, right? So this is a schematic of that sphere. This black circle is a sphere in d-dimensional space whose volume is exponential in d, right? So the volume of all possible regression tasks is exponential in d. Now, in the pre-training set, I can do the pre-training where I have a fixed set of unknown regression vectors. For example, maybe schematically 3 here, but in practice we use a lot more. And then we draw many, many examples, XY pairs from this one, XY pairs from this one, XY pairs from this one, and we train it to do the regression autoregressively, right? Now, if we don't have much data diversity, right, we might have a lot of data, like we might have a few regression vectors, but we have lots and lots of examples from this regression vector, this regression vector, this regression vector. So if we're in this data non-diverse setting, then if you ask what kinds of tasks can the system solve in context at test time, the answer is it can't solve new tasks that are very far from the training tasks, okay? So that's a schematic. These are the set of tasks that it can solve. You can see that they're concentrated near the training, the true regression vectors seen during training, pre-training, I mean, right? So maybe it generalizes a little bit, but it can't generalize over the whole sphere. But it turns out that there's a task diversity threshold where if the number of true regression vectors seen during pre-training exceeds a certain threshold, schematically it goes, say, from 3 to 5, but it's actually much larger, then you get a sudden transition where the transformer can now solve every single task in context as well as L2 regularized recursive least squares, which is the optimal algorithm, right? So this is the phase transition in the performance as the task diversity exceeds a certain threshold. And actually, a smaller diverse data set is better at inculcating this in-context learning capability than a larger non-diverse data set. So it's not just data set size that matters, it's the diversity that matters for unlocking downstream capabilities, which makes intuitive sense. Now, interestingly, how does the threshold scale with dimension? We see empirically that it scales linearly in the dimension. So here's an example of exponential capabilities, if not creativity, but capabilities unlocked by polynomial experience. Okay. Yeah.
Would this correspond to pruning in any way? Like you want the result of the pruning to be like such that when it generalizes, it covers the whole.
Oh, that's interesting. Yeah.
Like I don't know if it makes.
Maybe. I think the issue is here, if you start with a non-diverse data set, then pruning won't help. If you start with an overly diverse data set, then pruning could help or at least not hurt. Yeah.
Gotcha. Thank you.
Question. So this is really interesting. I was wondering, like, what is there an understanding of like what affects the epsilon distance around the original point?
Okay, so this is a purely empirical paper. I would say careful scientific experimentation to map out the phase transition, all that. It's all empirical.
But even
Yeah.
empirically, is there
Yeah.
a intuition on like what controls the size? In the sense that is there a way to think about if I what is the size of the epsilon if I wanted to cover the space I wanted?
Oh yeah, we did do an analysis like that. We compared it. I don't remember what that analysis told us. No, it's a slightly different analysis than the one you're asking for. Yeah, we don't have a this radius sort of increases smoothly with the number of pre-training task diversity below the threshold, and then there's a sudden transition at which it just suddenly covers the whole space, right? I mean, relatively suddenly. Yeah.
This is related to what you guys just discussed. That's the diversity.
Yeah, exactly. No, exactly. Yeah.
as a statistician, I would say that's the variance, right?
Yeah.
You have all of it covered in a complete diverse data set.
Yeah, except the pre-training doesn't have to cover the whole space before the in-context learning capability does cover the whole space. That's the surprising thing. Right, so this task diversity threshold, the number of unknown regression vectors you need to see during pre-training, need only scale linearly in the dimension. And then suddenly you can solve exponentially many new regression tasks in context. Right, that's the surprising part of it.
Yeah, I have a hypothesis. So is it related to linear independence? So for example, if you force this training sample to, like first W is focusing on the first coordinate, and the second focusing on the second one. So you will only be able to cover the whole D space until you have the W that's covered.
Yeah. So I think your intuition is close. I think it has to do with the fact that the target task is simple. It's linear regression. Now, you could say for a single regression problem, right? The input space is exponential. But we don't need to see exponentially many examples to solve one regression problem. We only need to see a linear number of examples. And that's because the regression task is linear, right? But the in-context learning is more complicated, right? If you see a bunch of examples, then recursive least squares has to do nonlinear operations on the sequence of examples to get the best prediction, because you have to keep inverting a covariance matrix, right? So this is a nonlinear algorithm in the input data, but still, the sample complexity is, or the data diversity threshold is linear in the dimension. We don't have a theory for that.
I guess because the diversity should be defined in different tasks. In the linear regression, it's defined in a way that, as what I said, the linear dependence. But if for some other tasks, the diversity should be defined in other way, maybe in a higher dimension.
Yeah, I agree, yeah. I'll have some speculations on the next slide related to that.
Yeah.
Just to clarify, these are all synthetically generated data sets,
All synthetically generated.
foundation data set selection.
No, yeah. We wanted to understand the question of when can a transformer really solve a new task that's completely different from its training set. And this, yeah. Well, okay, so the diversity comes from how many different regression tasks do we choose in the pre-training, right?
And also where they are, right? I could choose 5 that were all very close by there.
Yeah, so we choose them randomly. Yeah, so we didn't explore non-random selection. So all we varied was the number of random true regression vectors. Okay, but just a conjecture, like what might we learn in general for this? So a rough conjecture, and of course this needs to be made precise, a rough conjecture for the origin of exponential capabilities is that, the ability to answer questions, right, relies on learning some combination of skills. Like you might need to learn a little bit of history, you might need to learn a little bit of science. So like even within science, there's different branches. But anyway, there might be like a set of latent skills, right? And by composing these skills, somehow, you can learn to solve exponentially many possible tasks, like, I don't know, answer questions about history of science, or it's very vague, actually, honestly. But maybe only an experience that's linear in the number of skills seen during pre-training could allow in-context learning of exponentially new tasks, or just tasks in general, once you start probing an LLM. But can you make this picture of tasks and skills rigorous in some synthetic data set with exponentially many tasks, get more intuition about this far beyond the simple linear regression setting that we came up with? And then could we use this intuition to algorithmically decompose natural tasks into combinations of skills? Right? It's a completely open-ended research direction. Like, it's unclear how to do it, but I suspect it's sort of what's happening, right? But more generally, going back to the question of addition and multiplication, with math, we can solve exponentially many problems. But actually, we do it because we learn a finite set of skills. We learn a finite set of algorithms, and we learn how to deploy those algorithms flexibly in combinations to solve tasks. So I guess our mathematics, like just simple things like arithmetic and algebra, like that's what's actually going on, right? Okay. Yeah.
this composition?
Yeah, for our numerical work in regression, we just made the architecture expressive enough to get close to zero training error. We did explore variations in the regression case with architecture, and we found that we looked at variations in the number of parameters, attention heads, and so forth, and things scaled the way you'd expect them to. If you made it too big, it didn't generalize as well. If you made it too small, it didn't train, right? Like, so the usual stuff showed up there. Okay, so 12:45. Okay, I think I can actually finish both. Okay, so so now, so this was all quite qualitative and theory-free, right? This exponential creativity, except for the reversing the diffusion. I think that was relatively quantitative. But can we do anything quantitative with transformers? Like actually like predict performance on a realistic task or something like that? And it's hard to do for trained transformers, I think, but it's actually easy to do for random transformers that exist at initialization. And then you can use ideas from dynamic mean field theory and physics to understand signal propagation through random transformers. And that actually gives you intuition about what transformers do at initialization, and it helps you choose how to initialize them. And furthermore, you can use that information to predict performance at the end of training. So let's discuss that. So this is a very recent paper with a couple of physicists. Here's an example of being kind. This paper, Geometric Dynamics of Signal Propagation Predict Trainability of Transformers, we were inspired by some very good mathematicians at MIT who were trying to understand signal propagation just through multi-layer attention. And they had very rigorous mathematical proofs on what happens if you just have one attention layer, another attention layer, another attention layer, and you feed inputs through the system. And they could understand how that worked. But their proofs were so difficult that they couldn't generalize to attention MLP, and so forth. Right? We used heuristic physical techniques to do that generalization, and we could generalize the results and get qualitatively different results. I gave a talk at MIT with these people in the audience, and they loved it. They were so excited. In fact, they knew about the paper before I showed up. They were so excited to talk to me. They thought it was amazing. Okay, we submitted this for review, and it got terrible reviews in NeurIPS. Right? I think there were grad students who were expecting theorems and proofs. and so this is an example of where like people who are real theorem provers, they really appreciate the heuristics, but our young people don't. and so this is just an example of being kind. Anyway, I really like this paper, but I'll go through it here. So despite the negative NeurIPS review, I think it's a nice paper. And Philippe and Regule and Yuri Polanski also think it's a nice paper. All right. So here's the basic idea. We build on these elegant ideas of like, you have n tokens propagating through a transformer, right? So you can think of these n tokens in the embedding space as n particles. So if the embedding space is d-dimensional, the n tokens are like n particles in a d-dimensional embedding space, and they propagate through the attention layer, and the particles interact through the cross-attention mechanism, and then they interact, they go through the multi-layer perceptron, and so they change it. So you can think of this as a cloud of particles propagating through the system. And you could ask, as it propagates through this random system, how does that cloud of particles behave? Okay. So we analyze that. It's very difficult to analyze that for an arbitrary point configuration. So the trick we used was we used a permutation symmetric point configuration as the input. So this is the matrix of inner products. So yes, we have n particles, right? These are the n tokens, and we pick the initial configuration so that the cosine angle between all the particles, or the cosine, sorry. So this is the matrix. This is an n by n matrix of inner products between the particles. The off-diagonal elements are the cosine angle between the pairs of particles, and the diagonal elements are the norms of the particles. Right? And we pick a permutation symmetric matrix where the cosine angle between all the particles is the same. So they sit at the vertices of a regular simplex, and their norm is all the same. Okay? All right. So then what we can do is we can analytically using ideas from dynamic mean field theory, propagate this point particle through one layer of the attention and then one layer of the MLP. And if you start off as a permutation symmetric cloud, then on average, or at least with high probability, you remain permutation symmetric. So we can write down recursion relations for Q and P in one layer, how they translate to Q and P in the next layer, and so forth. So then we get a dynamical system on QP space, a discrete time dynamical system on QP space that illustrates how they propagate through. And now this dynamical system has certain phase transitions, okay? There's an ordered phase where the variance of the weights in the MLP, so the MLP has a sigmoidal nonlinearity, and so if the weights are small, it's basically a linear system, and it tends to contract the points. The attention mechanism also tends to attract the points, similarly to how n particles will gravitationally collapse to a point, okay? So in this ordered phase where the weights of the weights of the MLP are small, the MLP contracts the points and the attention contracts the points. So this dynamical system flows to a fixed point. Oh, sorry. P is the dot product, Q is the norm, so P over Q is the cosine angle. Okay, so this vertical axis is P over Q, so it's cosine angle. There's a single fixed point, and it's a collapsed fixed point, where the cosine angle between all pairs becomes 1, right? And the norm is finite. So basically what happens is if you have, say, 3 points at the vertices of a regular simplex, they'll propagate through the system and collapse onto a line. This is rank collapse that shows up in transformers if you don't initialize them correctly, and it's been shown in many other papers, okay? Our theory is quantitatively predictive. So this red curve shows the dynamics of the token angle P over Q and the token norm as you propagate through layers. And the blue histograms are what you see from empirical simulations of actual particles propagating, or actual tokens propagating through an actual random transformer with 16 layers, right? And you see that it collapses here, okay? But what if you now make the variance of the MLP large? Then in earlier work, the title was Exponential Expressivity and through Transient Chaos, we showed that if you have an MLP with large weights, the large weights will expand to nearby inputs, and then the nonlinearity will fold it. So you get expansion. If you just have an iterated MLP, you get expansion, folding, and that's a hallmark of chaos, where nearby initial conditions will exponentially diverge, but the norms won't exponentially diverge because of the nonlinear folding. Okay? So the large weights introduce chaos in the MLP, but the attention introduces a type of gravitational collapse of the particles. So you get gravitational collapse, MLP chaos, gravitational collapse, MLP chaos. And then what happens is you don't get the rank collapse. You get a bifurcation in this dynamical system as you increase the standard deviation, where the collapsed fixed point up here, where the cosine angle of 1 up here, is unstable now. There's a new stable fixed point. Sorry, I should have said this fixed point is stable. So if you start at it and you perturb away, you'll come back to it. This fixed point is unstable. If you start at it and perturb away, you'll flow away from it, and you'll come to this fixed point. This fixed point has a cosine angle that's not equal to 1. So the things are not collapsed, and there's another norm. So basically what happens is if you start at any regular simplex, you'll converge to a particular regular simplex. And that's what happens. That's a stable limit configuration of the particles. And you can see, again, theory matches simulations here. Okay, so let me, okay, so, okay, now if you also think about the backwards propagation, the back propagation of gradients, you can get vanishing or exploding gradients as well, right? So now you have a 2x2 matrix of whether the forward propagation is collapsing or not, and whether the back propagation is exploding or not, right? So you have these 4 phases, right? And you want to be at a phase boundary where you get neither vanishing or exploding back propagation, and you get neither, you're at the boundary of chaos in the forward propagation. And it turns out if and only if you do that, you get good training. So basically, I'm just going to go through this at a very high level. You get these two Lyapunov exponents that tell you how far you are from the two phase boundaries, the forward phase boundary between order and chaos, and the backward phase boundary between explosion and vanishing of gradients. So you need to tune two hyperparameters to be at the intersection of these two phase boundaries. And if you do that, that's where these Lyapunov exponents are 0. If you get them both to be 0, then you will train well, actually. And so that's necessary and sufficient for training empirically. So what we did here is this is a fit. So here are our two Lyapunov exponents telling us in hyperparameter space how far we are from the two phase boundaries. And then we train an actual transformer, and we ask, what is our test loss? Okay. This is an actual transformer trained on a toy data set of English, right? A big subset of English, a small subset of English. And this vertical axis is our test loss, the perplexity. So, is a test loss in prediction. And then we fit these coefficients. So if all you know is your Lyapunov exponent at the beginning of training, you can actually predict what your final test loss will be at the end of training. And you see that you only get good test loss if both are 0. Right? So that's a fun sort of thing where we can actually say something quantitative about signal propagation through transformers, and it has an impact on performance. Okay. So then just some fun stuff on connections. Okay, so I have 3 minutes left. I'll go through this quickly. Some fun stuff on connections in neuroscience that Umesh suggested I talk about. So let me skip the history of this field. So basically, the basic question is like, okay, now that it's not that important. So here's the basic question. Because I know lunch is next. I don't want to stand between people and food. I know I'm in a precarious spot here. The basic question is, we have these large language models, they process language. We have brains, they process language. What's the relationship? Well, you could do something very basic, is you could try to measure neural activity in humans through fMRI, through MEG, or through ECOG data. And you could try to just regress neural activity in the brain against neural activity patterns in an LLM processing the same language, right? And various people have played this game, and they get a remarkable match, right? Huh? They have data for that. Yeah. So it's you put humans in an fMRI machine, and you ask them to either read language or hear language, and then you measure neural activity patterns in Broca's area or Wernicke's area that process language. Or yeah, so you're collecting from humans, so it's order thousands of words, right? But you don't need the corpus. You only need a corpus of a size that's sufficient to solve linear regression from neural activity patterns in a pre-trained LLM to voxels, fMRI voxels in a human, right? So thousands of words is enough for that. Oh, okay. So you have an LLM, so it's processing the same language, so it's doing autoregressive prediction. And then you have neural activity patterns in some layer of the LLM. So for every word, in every given layer of the LLM, you have a vector of neural activity patterns, right? Just the embedding vector. Now, while a human is processing that word, you have an fMRI voxel. So you have a voxel that has a time series, but it's also some pattern that varies from word to word, and it depends on the context as well. And then you have a vector in the LLM that varies from word to word. And so you just regress this scalar variable against this vector. And you ask, how well can I predict that scalar variable? And then you do it for all the different scalar variables, all the fMRI boxes in the brain. And you get a map of how well you can predict activity in the brain from the LLM. That's the basic setting. Now, this is not something new. It's a game that's been played every time we had an advance in machine learning. Whenever you have an advance in machine learning, you ask, how does that advance in machine learning relate to the brain? And there's a big, long history of that. For example, one of the earliest works on this appeared in 1998 in Nature. When you move your eyes, there's areas in your brain called the parietal cortex that code not only where things are, but where your eye is in a complicated manner that was hard to understand. Right? So for example, like the big problem that the brain has to solve, if I move my eyes, I don't think that if I move my eyes right, I don't think the entire world moved left, right? And if I want to reach for my microphone, if I'm looking this way, I can still reach that way. So the brain has to code objects in the external world in a global coordinate frame. But no global coordinate frame exists at the sensory periphery. I just have patterns of photoreceptor activity in my retina and knowledge about my posture. So how do I combine photosensory inputs and postural information to construct a global coordinate system so I can reach for this as I turn my head? Right, this starts to be solved in the parietal cortex. And what they did is they trained a 3-layer neural network to solve that problem. It has eye position, head position, and it constructs global coordinates. And the intermediate layer behaved exactly like the brain. It was very cool, right? So this kind of started that off. You can do this for the retina. We actually played this game for the retina as well. We asked what would an optimal retinal processor of natural movies look like, and it looked exactly like the primate retina with all the different cell types. Since we're at Berkeley, Bruno's here. When sparse coding came about, people were wondering, why do we have edge detectors in our primary visual cortex? Well, sparse coding develops these edge detectors, and it has a similar statistics to what the brain develops, suggesting that the normative goal of V1 is to do edge detection. Coming to more recent times, Dan Yamins did some really nice work where high-level semantic representations in inferotemporal cortex and V4 that are very sensitive to like faces and other objects and things like that. Nobody could have come up with a model that goes from pixels to neural activity patterns deep in the visual cortex of the brain. Dan Yamins was the first to do it, and the way that he did it is he didn't try to predict neural activity patterns from data by directly training a model. There wasn't enough data. So he trained a model on ImageNet, and he regressed neural activity patterns from different layers of the ImageNet trained model against neural activity patterns in the brain, and he got the best models of activity in the brain from the ImageNet models. And so this game has been played over and over again, and these are nice works that have played this game in language. So again, as I was explaining before, they take LLMs, and they use the activity in the LLMs as it's processing a sequence of words to predict neural activity patterns in the brain as the brain is processing the same sequence of words. And they get pretty good predictive capability up to the noise level. But these measurements are also quite noisy. And the negative perspective on this, which I think is overly negative, could be just that, well, the LLM is creating a very high-dimensional set of basis functions over word sequences. And so if you have a high enough dimensional set of basis functions, obviously you can combine them to create any function you want, including functions that appear in the brain. But there's lots of other stuff that might rule out that kind of negative interpretation of it, but that always lurks in the background. Okay, and then, oh right, there was one work that we did where few-shot learning, we showed how to use these representations to few-shot learning. I won't discuss this at all, but if you're interested, this is a fun paper, and it actually connects to language. We could solve problems like, if you get we could show just a super high level, we could show that neural networks did few-shot learning as well as monkeys did if you had access to the monkey's brain representations. So we compared deep networks to the brain, and we could also do zero-shot transfer from language to vision. Like if I give you a text description of 2 categories, and then I give you 2 images and ask you which one came from which category, we can solve that problem. So can super simple language and vision models when you put them together. And we have a theory for how they do that and so forth, and that's in there. And then I'll stop here. Thanks.
Questions a little bit out of the scope of your talk, but I think you probably have interesting things to say about it. So part of the talk we were talking about whether we need the data, so explaining how much data we need, and the connections with the diversity of the data. Okay, so one goal is that we take the minimal amount of data in order to still be able to be creative. And another goal, that at the same time we want to be somehow resilient.
Oh yeah.
And then, possibly there is value to having more data, to not just going for diversity.
Yeah.
And I wonder if you put that into the equation, how the theory would change.
Yeah.
My assumption is,
Yeah.
in the brain for sure, and we have to account for that.
Yeah, it's a really good question. So the basic thing would be resilient to what change, right? So there's a whole field called out of distribution learning.
No, right?
Yeah, we don't know. Yeah, yeah.
A class of possible attacks.
Exactly. Yeah, yeah. So there's this whole field called out of distribution learning, where basically the test distribution is different from the training distribution, right? And that's a much murkier field. There's various techniques to deal with it. None of them are super great. There's no good theory for out of distribution learning, because you have to have a model of what the shift will be. But I think that's absolutely key. Like I think a hallmark of intelligence is our ability to not just generalize on the same distribution as the training set, but like the training set changes completely and we still figure out how to deal with it, right?
I'm saying not even just that the input changes, but possibly even your machinery gets damaged.
Oh.
And,
oh, I see.
As you are training on more data, possibly you are accounting for the fact that maybe some portions of your machinery will.
Oh, yeah, yeah. Yeah, 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 yeah. Yeah, I mean, that actually happens in our brain. We have a lot of turnover and things like that. So actually, yeah, so.
And there's an activity, there's plasticity, right?
Yeah, yeah, yeah.
Not counted.
Yeah, that's true. Yeah, that's true. In machine learning, we usually don't model that because we have access to digital computers that don't change. Right? Like we can store bits stably. Yeah, yeah, yeah. Yeah, and also adversarial machine learning. Yeah, that's another very murky subject. Actually, my former grad student, Stanislav Fort, had a really nice paper on defenses against adversarial examples biologically inspired. So what he did was he had a multi-level visual system with saccades and noise and diffusion. So the system was always changing over time. So it's harder to attack it. Like we have fixational eye movements that are moving around all the time. We have saccades. Yeah, and it turned out that was, he implemented a machine learning version of that was more robust to adversarial attacks. And Ian Goodfellow actually really liked it, actually. So he's visiting me, and I'm having him a group meeting to my group on that. But that's, a lot of people have said this is one of the first examples that might be a really good defense against adversarial attacks. Stanislav Fort, look him up. He's a really great guy. Yeah.
A question going about the diffusion models. You mentioned that if you're too good with this backward diffusion, you always get back to the training data.
Yeah, yeah.
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 And so, is there an optimal way of kind of making errors so that this that generated data is kind of meaningful?
Yeah. So probably.
Accurate, follow the diffusion path.
Yeah, there's a trade-off between memorization and creativity, right? You definitely don't want to memorize, but then if you're going to be creative, in which ways are you creative? So I think that's very much an open question. I think for simple systems like MNIST and Fashion MNIST, spatially local creativity is like mixing and matching different training points in different parts of space is enough to explain what a trained UNet does. The UNet has the locality, so I think that's a good inductive bias for images. But more sophisticated versions of it also have the attention, and that's learned. So I think that's a big mystery, is what does attention do in diffusion models? We're going to be working on that next.
Your data curation or pruning with the pre-trained foundation model is like kind of very similar or inspired out of synthetic data. Like
yeah. Yeah. That's a dream of all these companies, right? Because they might be becoming data bottlenecks, probably are. And so can you generate synthetic data to get around that? There are, I just wrote a grant with some people from MIT who have some nice results. Philip Isola has something called SynClear, where he uses generative models to generate synthetic data. And he shows that if you train downstream generative models on the synthetic data, they do as well as on real data in a variety of downstream tasks. So that's the first example that I've seen where synthetic data does something useful. But there's other work where if you keep doing this iteratively, the whole thing degenerates, right? So I think when synthetic data helps you or hurts you is a major open question, both empirically and theoretically. Sham Kakade has some nice work. I wrote a grant with him. We all wrote a grant together, and Sham Kakade has some nice work called Transcendence, where he takes a bunch of chess players with low ELO scores. And he learns a policy based on data from all the chess players with low ELO scores. And then he lowers the temperature of the policy. And that policy the lower temperature policy has a higher ELO score than any of the training points. He calls it transcendence. It's a very catchy name. So if you Google Sham Kakade and transcendence, I think that's a nice paper. And he has a theory for why. It's a bit like boosting, right? Where you turn a bunch of weak learners into a better learner by majority vote, right? Which is lowering the temperature is like doing a majority vote. So it's a very nice theory, a very simple theory actually, but it's very nice. But I mean, synthetic data for generative models is a much more complicated scenario.
Yeah. So another question. I'm not sure if you want to answer before lunch. So about your the different communities and
Yeah.
use language. Yeah, I think that's.
See, you and I come from different communities, but we get each other. I think you're very kind.
Some papers using statistical mechanic.
Okay, great.
But anyway, I'm curious. I mean, other than the reviewers, I mean, what should we change in the way we train students to?
Oh, it's a fantastic question. It's a really fantastic question. I mean, it's very hard for a student to pick up so many different techniques by the time they graduate, right? I think at least we expose them to different ways of thinking and we educate them in different ways of thinking, if not the techniques, the technical techniques and in the different ways of thinking. And we kind of change the culture at the level of people coming into the field. Some of us old people might be too hard to change, but you know, I think that at the very least, we want to inculcate this culture of many ways of knowing, right? I think, at the faculty hiring level, that's another issue because we're stuck with departments which are a relic from the Middle Ages, right? So a stats department is not going to hire a physicist. There are these data science institutes that are much more open-minded. So hiring at institute levels might be more flexible. But oftentimes in many schools, they have to end up in a department and the department has a very stringent criteria of, are they one of our own? Right? Like I ended up in a physics department because they viewed me as one of their own, right? But an applied physics department. But I love it there actually. But I would actually be happy in a double E department or a stats department, like if they would take me, you know, but I'm happy where I am. So but yeah, these are all interesting sociological issues, probably discussed over beer. But I think those are the two key knobs: faculty hiring and grad student training. And then lesser knobs, but important ones are reviewing and calls for grants also, like these interdisciplinary calls that are willing to take many different types of people working together.
Thank you.
Okay, thanks.